Good afternoon, everybody. Yes, as the thing says, I'm talking for Peter Ellis for work that Peter actually did. So you'll have to bear with me because I've had to try to interpret Peter's notes in an hour and a half presentation that he put together that I've tried to shorten down to 20 minutes. Unfortunately, Peter can't make it because he was involved in a fairly serious accident. He's recovering, but the recovery process is going to take a bit of time. So we're hoping that he can get back to us fairly soon. So this work is a component of the Bushfire CRC project that Matt was talking about. So the CRC project was fire development, transitions and suppression, and it was also connected to the work that Robert reported from Will Thurston. So there is a sort of a method to madness, and it all connects together. So what are spot fires? Spot fires are those fires that are ignited by a firebrand sourced from another fire. They occur predominantly in forests, but can occur in grasslands and other fuel types to various degrees. Generally, they're pieces of bark detached from burning trees and lofted in a convection column, as Robert sort of described. And they're transported by the wind field and may land, alight and start a new fire. The firebrands can be other things other than bark. They can be twigs, leaves, fruits, seeds, and even dung in the case of grass fires. Just as an illustration of the difficulty of dealing with embers, this is a video that was taken during the ACT fires by Wind News on the afternoon of January. Most of the embers that you see are actually sourced from vegetation, there's a passage here that goes around the corner, and the car's probably doing about 35, 40 miles an hour over the time. And then just keep up with it.
SA3 to Bravo 3. Camera 10, camera 20.
Anyway, so there's these embers in real life. Here we've got a schematic diagram that sort of shows our understanding of the processes involved. So we've got a fire burning up across some topography. It's come to the top. It's got a big convection column. Firebrands have been sourced from a tree. They flow up in the convection column, as Robert described. At some point they fall out. If they fall out of the convection column before the firebrand actually stops burning, then they're likely to start a new fire. If they go up high and then fall out, they may stop burning before they hit the ground, and so there'll be a dead ember. So there's been a little bit of work that Peter Ellis has done previously in understanding what the aerodynamics and combustion characteristics of the firebrands themselves are, and primarily looking at stringy bark types, bleakfir and jarrah. The work that Will Thurston's doing is looking at what's happening inside the convection column, and the work I'm going to present is stuff that Peter's done to try to determine what the probability of a firebrand in the ground actually initiating a successful fire. So two key questions that drove Peter's work are, what are the conditions necessary for a successful initiation by firebrands of spot fires? And can a glowing firebrand with a mass less than 0.1 grams ignite a spot fire? So the embers that we saw flying around in the video were about that size. The approach was a laboratory investigation, looking at the ignition of a fuel bed that's common in devastating fires by samples which have the characteristics of small common firebrands. And the things that we were varying were the fuel and weather conditions. So mainly moisture content and wind speed. So the expectations were that there'll be similar patterns of ignition probability to fuel moisture for Euclid letter that Matt did for his honours work a number of years ago, allowing for differences in a different ignition source. Matt used, what was it? Cotton wool balls soaked in methane. So here we're actually going to be using vegetation, or vegetative matter. And there was a series of experiments done in France that used glowing firebrands, but they didn't find any response to fuel moisture content in their work. So the fuel bed that was used in this study was a well-developed litter profile from southern tablelands dry sclerophyll forest. Dry sclerophyll forests are implicated in a number of devastating fires, including the Kilmore East fire. They contain notorious spotting species, and they're fairly widespread throughout Australia. The fuel beds themselves were 400 millimetre by 400 millimetre samples taken in situ. So Peter designed, I'm still waiting for the patent application to go in, of this tool for actually lifting up the litter bed intact and placing it into a tray. 48 trays of similar fuels were collected from 2 sites around the ACT, Cohen and Googong. So the fuel was transported and characterised for fuel component, leaf, bark, twig and surface roughness for airflow, and conditioned for FMC all inside the tray, so it was never touched again. Each tray was divided into 9 ignition test sites, and there were a total of 432 potential ignition tests. So there were 2 standard ignition sources that Peter used. One was a flaming ignition source and the other was a glowing ignition source. The flaming ignition source was actually a satay stick, because he found that was the most consistent source of firebrand that he could find. It was cut to 50 millimetres length, it was 2.4 millimetres in diameter, and it was equivalent to a twig with a 3 to 4 metre per second terminal velocity. These were oven dried to 5%, ignited for 3 seconds using a propane torch, and then dropped into the test site. The placement was random within the test site, and the sample itself, once you turned off the propane torch, would flame for about 9 seconds in still air. The glowing source was equivalent to a small firebrand with a terminal velocity of about the same as the flaming source. He had a significant amount of problems trying to find one that wouldn't reflame by itself, and ended up using an actual piece of bark from globulus that was a 50 millimetre by 15 millimetre rectangle with a hole drilled in the middle of it that enabled him to put it at its terminal velocity, which I'll show in a tick. So these were burned at their terminal velocity for 12 seconds, and then when they were dropped onto the fuel bed, they had a mass of about 0.2 to 0.25 grams. Again, their placement in the test site was random, and they glowed for about 2.5 to 3 minutes with the presence of wind. So here's a video, an early video of one of his sort of test burns that he did. This device here is connected to a vacuum cleaner, and that allows him to mimic an airflow over the firebrand, which provides the terminal velocity. So the firebrand was ignited, strung onto this steel rod, then spun around inside here at its terminal velocity for the period to imagine that it's gone up and down, and then it was dropped onto a fuel bed. So you can see the firebrand glowing. He did this all himself, so he's got to move the camera, then he's got to turn the fan on. So there's the firebrand sitting in the fuel bed. Now he's got the fan going. And you can see it starts to glow and actually consume. So the red area is consuming the charred bit. And then you'll see the fuel around the firebrand actually ignite. You would then have to try to put the fire out before it burnt the rest of the fuel tray. Quick people. So in the actual experiment, he built himself a wind tunnel. The intent was to actually use the pyrotron, but it was too big for his purposes, so he ended up building a wind tunnel that was about that wide, big enough just for the fuel tray to sit in. Fan at one end, some straighteners to improve the airflow, and then he measured the airflow in the tray and also correlated that with airflow measurements that he did out in the field. So you can see one of our very expensive 3D sonic anemometers sitting upside down in the lab. I'm not too worried about that. One of our very expensive 3D sonic anemometers upside down in the field, a little bit more worried about. He didn't break it though, which is good. Oh, there's one at the top as well, so measuring 2 metres height and then like 5 centimetres above the ground. So the variables that he was looking at were the glowing and flaming samples, wind in the tunnel, wind velocity. He had no wind, 1 and 2 metres per second. He measured the turbulence in the airflow, moisture content of the firebrand sample, the fuel moisture of the tray, the temperature of the fuel itself. In the field, he found that the temperature was around 40 to 50 degrees C, but in the laboratory, without the solar radiation, it was about ambient temperature. And the ambient temperatures were around 30 degrees and 25 to 45% RH. He found RH was the biggest problem in the lab, trying to get it controlled. So the experimental procedure that he used was tray divided into 9. He would then drop a firebrand sample at random. Its orientation of the tray within the wind tunnel was random. The flaming firebrand tests usually went for about a minute before he put it out, and the glowing firebrands went for 2.5 to 3 minutes before it was either successful or not successful. He measured the time to flaming ignition, and he put out the successful ignitions with a little can of CO2. And then it either got a 1 or a 0, 1 for successful, 0 for not successful, and then used logistic regression to analyse the data. So here's just a photo collection illustrating the ignition process. So we've got a glowing firebrand that's been dropped onto the fuel bed. So these are every 1/10 of a second apart, these. So we can see that with an airflow, I'll go back a step. The firebrand has been charred in the ignition process. That char itself is actually combusted in the glowing process, and it leaves behind a white residue. The black char can further combust through glowing combustion. The heat yield for glowing combustion is about 30 megajoules per kilogram, compared to flaming combustion, which is about 14 megajoules per kilogram. So there's a lot of heat that comes out of this glowing combustion. And you can see, depending on the orientation of where the firebrand lands inside the fuel bed, a element of unburnt fuel may be in close proximity to the firebrand, and in this case there's a twig here that eventually ignites and has a successful ignition. So what he found was, in the flaming firebrand, it always resulted in initial flaming ignition, but its subsequent propagation, so whether it actually initiated a fire, was determined by both the fuel moisture content of the bed and the wind. In the glowing firebrand, it required a very low fuel moisture content plus optimum placement of the firebrand in the fuel elements, driving its exposure to the wind and the turbulence in the wind that determined whether it transitioned to flaming or not. If flaming ignition did occur, it was sustained only because the fuel moisture content of the fuel bed was low enough to actually allow it to happen. So here's some results for flaming firebrands. This one is a no-wind case. Interesting points to make here are that above 15% fuel moisture content, there was no successful ignition whatsoever. You started to get successful ignitions at around 14.5%. About 50% of the ignitions were successful around, what's that, about 9% moisture content. And then below about 5 or 4%, everything ignited. If we compare that to a wind case, what's happened is that the transition has been driven to a higher moisture content. So here the transition starts at around 20% and 50% occurs around 12 or 13%. So you need less. You can get a successful ignition with a higher moisture content if there's a presence of wind for that flame firing. And here's just a comparison of the model against the data that is to develop that logistic model with an R squared of 85%, which isn't too bad. I just realised I didn't put any glowing results in. You'll have to forgive me for that. There is a result, there is a model for glowing firebrands, but I didn't put that in. Anyway, glowing firebrands, comparison, so they're the threshold values I sort of pulled out before. In comparison with other results that were found, what Pete found was that the thresholds are lower than what Matt found with his work, but not that much different from what the US National Fire Danger Rating System uses. So it's a good sort of confirmation that the results they're getting are quite good. In conclusion, it's found that the models that he developed estimate the likelihood of spot fire ignition in well-developed good profiles. You've got to have that full bed of data, because that's what he was using. And he found that small flaming of glowing firebrands under relatively mild temperature conditions in RH and levels of turbulence was quite important. Prediction during extreme or catastrophic FFDIs could be served for using the curves corresponding to the upper confidence limits of the model. And the models could be applied to less well-developed litter fuel beds by employing a factor that actually includes either the VESTA fuel guide or the overall fuel hazard guide percentage cover or hazard score. He's found that he needs to study the effect of the solar radiation on the heating of the fuel bed, and also winds with comparable variability in turbulence to what he measured in the field. So turbulence at the fuel surface in the forest is very important, and we need to be able to reproduce that in the laboratory. And there's an apparent different pathway of transition from glowing to flaming ignition. He found that he wants to investigate further. So in answer to the questions that he started with, what are the conditions necessary for initiation by firebrands? Modelled as a function of fuel moisture content and wind for this undisturbed fuel profile, and for a characterised airflow. So the airflow he was using in the wind tunnel was fairly laminated. It wasn't highly turbulent. And can a glowing firebrand with a mass less than 0.1 grams ignite a spot fire? Yes, was the answer to that question. Thank you. I'll do my best to answer questions.